So welcome everyone again to Brocade. I'm planning to speak on WAN virtualization, uh, especially when it comes to who's spearheading those projects. We see certain market trends, very definitive market trends on who is adopting OpenFlow SDN in a big way, uh, primarily driven by certain funding requirements, both from the National Science Foundation as well as BTOP funding requirements. So there are certain market segments which are very receptive to SDN and OpenFlow, and there is a definite incentive to implement them on a wider scale, primarily driven by research and education networks. But also what we are seeing is to do that kind of investment, to do that kind of implementation of SDN OpenFlow with these platforms, there is a big push to virtualize the WAN itself. Instead of virtualizing the data center, which is a second segment of SDN and OpenFlow and software-defined networking, I'm gonna concentrate on WAN virtualization, where we see the market going, what is required to virtualize a WAN, and where we are seeing what projects. The idea is to give you what projects are going on, how they are being implemented, and what is really affecting or what the requirements are. The requirements are pretty unique compared to data center requirements. So you will be able to compare and contrast where the investments are being made, where the rollouts are happening, as well as compare them with the data center OpenFlow requirements as well as implementation. From Brocade's point of view, we are spearheading the SDN OpenFlow project through our flagship router platform, which is the MLXe, the NetIron MLXe platform. And primarily, this platform is in production for over a couple of, maybe 5 or 6 years, 30,000 routers shipped. There's very high install base of IP and MPLS in both WAN as well as in LAN segments, primarily driven by Level 3 and Hurricane Electric. Those are the primary backbone providers where this platform is installed, as well as a large install base of internet exchange points, like Switch and Data, like Equinix, like Amsterdam Internet Exchange. We see petabytes of data going through them, primarily driven by two factors, OTT, over-the-top video, and also a large amount of research and education data coming out of, for example, CERN and Fermilab. Especially when they did the FTL, or faster than light particle detection, the jump in the data for big data as well as genomics, it rose up very high. And we see that those two combinations are actually choking the WAN at certain given points. Now, if you look at backbone networks, their capacities are primarily driven by two factors: the installation of cable, high availability, as well as the capacity of the cable and the length of the cable. So in case where the lengths of these cables are up to a certain distance, for example, either transcontinental or transatlantic, we see those cables are primarily responsible or capable of doing high-speed networking, which is primarily driven by 100 gig. But if it comes to the length of cable across Trans-Pacific, those cable lengths and repeaters and amplifiers are not capable of doing 100 gig across those. So there, on the WAN side, they're looking at 40 gig on the WAN. But when it comes to the continents itself, there is a big push going on 100 gig. And when you do 100 gig on continents and you're trying to give an OpenFlow or SDN-based solution, there are a number of challenges when it comes to giving that solution. That bandwidth is primarily, there's a competition for both traditional IP network, MPLS network, or existing service, as well as the services which are going to be programmed, meaning programmatic API services through SDN, through OpenFlow. And the efficiency is to who is going to get the control. Hence, there is a discussion of high availability of controllers, competition between MPLS networks versus SDN OpenFlow networks, who is going to derive or who is going to be doing the bandwidth or who's going to have the right of way for that bandwidth, and how you're going to create a access solution which will allow for both parties to exist simultaneously. So that is where the hybrid mode comes in, either a hybrid port mode or hybrid switch mode. Those kind of technologies come into the picture. So I would like to go and give you an example of what we have done so far. Internet 2, which is a primary example of spearheading WAN virtualization, especially when it comes to SDN and OpenFlow and innovative services, primarily driven by CC and IE grants. But they have rolled out two services. One is to give a 100 gig backbone across the nation, and also to make it more programmatic. So it is entirely based on SDN OpenFlow control. And in this case, Brocade has been installed in the backbone. Multiple nodes in the backbone, multiple distribution points, both in Manhattan as well as across the nation. So this is a prime example of who's using us for the SDN OpenFlow backbone. Now the question comes in, who's going to be in control of this backbone? So what we did was, we actually worked in collaboration with the controller software which was going to be used on this platform, primarily the Indiana University's OESS or OS3E platform. This was derived from an open controller called the Knox. The web orchestration software was done, and the idea was to give the same level of functionality for high availability and high reliability which is expected out of a service provider network. For example, if you have multiple paths across your WAN infrastructure, how do I do a protection? How do I do switchover? And how do I guarantee when a big data traverses the network, I do not intervene from an IT point of view? So automatic reconvergence of network when the big data is going on for multiple hours, 3 hours, 5 hours, whatever that case may be. Okay. It was essentially a layer 2 based service for now, with layer 3 and MPLS based service coming later in point, depending on what the uptake is. The other two projects which are going on right now are the Genie project, which is actually done by about 46 universities. They have a Genie racks, essentially a solution which allows for programmatic control as well as for proactive programming of flows on a device. On top of that, all these universities also want a unified structure to acquire an OpenFlow based platform. So that is done through an organization called Quilt. And Quilt allows these organizations to get an OpenFlow solution based on approved vendors. So there's an approved vendors list which allows multiple of these universities to go and get a checklist of not only hardware vendors but as well as software vendors. Okay. Now, what does this platform offer? I mean, what are the requirements of this platform? First of all, it has to be flexible control. That means either I can say do multiple controllers are in charge of this network, or I can say I have a proxy controller which will have multiple controllers sitting behind the proxy controller. This is all related to high availability of these networks. They also want control on the flow of the network, whether it is fine-grained or aggregated, meaning that a flow defined in an OpenFlow SDN-based network can be based on, let's say, MAC, can be based on VLAN, can be based on host, can be based on the granularity of what is required to be controlled over here. They can be based on IPNet or IP subnets or IP host itself. So both of the controls are required for these kind of projects, as well as they have to have what we see as a wire speed performance-based networks, which is able to give you high number of flow modifications required on WAN per second. Now the reason I say that is because if a controller is sitting, let's say, in Indiana, or a controller is sitting in San Francisco, and he is trying to optimize the whole WAN network, he has to go hop by hop on SDN network, which was primarily done by IP or MPLS-based network before. In this case, the controller is in charge of doing this configuration throughout the WAN. What we are seeing is it requires certain amount of delay as it goes and configures the WAN itself. What OpenFlow standard doesn't address is how many such flow definitions can I modify simultaneously across a wide area network. That is a point where the speed at which these modifications happens throughout the backbone come into picture. Also, the number of experiments, whether they're related to telehealth, whether they're related to telemedicine, whether they're related to genomics, whether they are related to analytics, whether they're related to big data. These experiments have certain needs. And those needs are, they have to be based on the type of experiment, on the location of experiment, and the topology of experiment itself, whether they're point-to-point, point-to-multipoint, a tree-type distribution service. All those things have to be also analyzed on an OpenFlow network. And lastly, how do you avoid controller congestion? Meaning that now you have a definite point in this network over a WAN where a DDoS attack can happen and can take your network down. For example, if I attack your proxy OpenFlow controller, or if I put a denial of service attack on all the controllers itself, then I can actually deny you access to the network. So in this case, how do I protect the controller as well as how do I not allow the controllers to get congested? So in case of OpenFlow, there are certain rules where you say, when the flow comes in, send it to the controller, or when the flow comes in, program it on your network. What this platform allows you to do from Brocade's point of view is we do recommend a proactive creation of rules when it comes to OpenFlow SDN, meaning that those rules or those flows which you decide to program the WAN will have to be programmed first, and then the flows can come in. If you do a reactive model of flow, meaning that a flow hits your WAN, SDN WAN network, and then you go to the controller saying, hey, Mr. Controller, what do I do with it? You are actually opening up a possibility of congesting the controller, whether they are in a controller farm or whether they are controller customer. The primary driver for SDN in Americas is primarily driven by CCNIE grants. And these grants, we see that certain states are prone to putting their infrastructure, the campus infrastructure, the university infrastructure. These are primarily driven for a science DMZ project, regional optical network, as well as university campus network. That's where the greatest uptake is on the SDN OpenFlow side. In case of Japan, the Japan Internet Exchange, or JGNX, is primarily driving most of the WAN virtualization in that particular space. There are multiple universities connected here, but the difference here is they are looking at an OpenFlow network which is driven by 3 different control planes, whether it is a DCN, data control plane, OpenFlow plane, or virtual node plane. They want all 3 to exist simultaneously on top of an existing IP MPLS network in the WAN. What I've given here is an example of what that WAN infrastructure looks like, meaning that these are the Lambda flows on the fiber infrastructure itself in Americas. And this is what needs to get virtualized first, even before we go and talk to data center virtualization. Data center is located inside a particular location at a given particular city. We are not talking about how do we virtualize the infrastructure itself. So what we are trying to do over here is identify the locations at which these co-location points exist and identify whether they can be virtualized on WAN with an OpenFlow support or not. So this is how a research network flows come in. Most of them are coming in from either LHC experiment or Atlas experiments, or they're coming in from Fermilab.
How many nodes are hanging off of that network approximately?
Roughly, it's around 50 locations or so.
Yeah.
So in each location, can be considered like a co-location facility, and whoever wants a drop point usually adds a router at that point. For example, if entity A says I need a router, then the backbone provider, in this case, will either give a Lambda handoff or a dark fiber handoff, and those handoffs can then be distributed across whichever parties are interested. So on a co-location facility, you do have to virtualize both your WDM infrastructure, as well as you have to make your routers, which are hanging off of this WDM infrastructure, also OpenFlow capable. For example, this is what the infrastructure looks like in APAC. In APAC, we are tracking a lot of Lambda insertion points, and most of these insertion points are in, they are looking at OpenFlow SDN. They know what it takes to virtualize, but they're looking at essentially the WAN virtualization which is happening in Americas. In case of Australia, most of the WAN virtualized networks, most of the WAN virtualized network over here are going across Trans-Pacific. The Trans-Pacific fiber lines, if you want to virtualize them, the problem is the length of the cable itself. Here, most of them will be 40 gigabit as opposed to 100 gigabit. The point over here I want to make is the program, which is, as you might have heard, Square Kilometer Array Project, or SKA project, is well into installation phase. The fibers have been laid out. The telescopes are there. But it is going to generate a huge amount of data. And they have to also transport that data over this existing infrastructure. And in case of Europe, primarily we see FTL and neutrino projects coming out of Geneva from CERN. And the distribution is driving what we know as science DMZ projects for distributed computing. And those projects are the ones which are actually using OpenFlow as a mechanism. And the interesting use case is your firewalls cannot handle big data, and your firewalls cannot handle the rate at which these guys want to connect with. For example, 10 gig or 100 gig connection. So entire science DMZ is based on that.
Do you know if Tim Bell's building 3 new 15,000 node data centers for the supercollider at CERN, all based on OpenStack? Or is there any talk about integrating those OVS, the switching layer, into this network? Or you know, if it rides up?
We are installing the backbone for CERN.
Okay, there you go.
Colin, I can tell you that there are places that are going to attach to that are already expecting to get data out of CERN on it.
Right.
So they're as soon as those suckers come online, they're going to be pumping lots of bits down the wire. So the node that swings through Tulsa, that's one of my customers. We're looking at how we're going to split that off and hand it off to the universities there in Oklahoma. And we're looking at pumping 10 to 12 gigabits of traffic from the National Weather Center back up to some supercomputers to crunch it down to do better forecasting models.
That's interesting.
And then down in Brazil, this is an interesting place where Brazil is primarily driven by funding both from Europe as well as from US. And we are seeing a lot of interest in Brazil to virtualize and do a programmatic control to their international connection. I think they will be the first ones to drive the OpenFlow across the ocean. And they're well into implementing OpenFlow on a transoceanic cable. Very interesting use case also over here. And why do I bring this out? Is because in all these WAN OpenFlow infrastructures, there are two things: elephant flows and mouse flows. When it comes to big data genomics, it doesn't matter which experiment you take. The elephant flows are where they tend to persist for a long time. They're primarily used for distribution. And your campus networks and all other networks which also use the same infrastructure are what we call mouse flow, emails, HTTP. And they kind of have more control over the elephant. So that's why I have a picture of this mouse holding an elephant. But what we are seeing is the OpenFlow SDN network has two primary challenges. How do I deliver elephants, and how do I control my mice from running around? So that programmatic control has to take into account both the flows. And when you deliver all these big data or genomics type file structures, the current infrastructure, which is based on link aggregation, will have a problem delivering these elephants to the destination, meaning that they deliver these big files and the elephants might arrive in a different format. They are broken, sometimes they are out of sequence, sometimes they cannot be recollected, they can be put together. So there is a lot of retransmission and workarounds putting in place to collect all these elements. So transition to 100 gig, transition to OpenFlow, and bypassing the firewalls is essentially going to help the DMZ projects putting these elephants back together. Now this is an idea of what that DMZ might look like, what the transition phase might look like. The backbone networks in the center, the Internet 2 networks, they are providing OpenFlow via the AL2 or Advanced Layer 2 Services network. And this is primarily a Layer 2 based network which is under control of controllers based out of Indianapolis. And these primarily go into regional optical networks, primarily based in each of these states. And once the regional optical networks get this data, they distribute it to multiple campuses in either high energy physics, high energy chemistry, or biology departments. So this is, I want to lay out what that would look like. And the reason I bring this up is because some of the telehealth initiatives or the genomics initiatives, for example, Gene by Gene company, which actually allows you to sequence a gene. All you have to do is, plug in your a little poke device, take a sample and send them in. And then they can do what we call as data in rest or data in transition. In this case, they might charge you a few $100s to figure out Parkinson's, Alzheimer's, whatever diseases you might be prone into according to gene map. Or you can ask for a whole range of medical issues which you want a gene map to be mapped for. And this is what is primarily driving this network. The costs of these experiments are coming down drastically. They used to cost about $10,000 plus for a sequencer. Now they are under $1,000. And I am expecting that it will go significantly lower in coming years. So all these things have to run on this type of network also. All right, so what does this network look like? Where does OpenFlow fit in? How did OpenFlow got fit in? I think the questions might be, why did National Science Foundation look into this in the first place, right? They wanted to enable this kind of innovation in multiple places, not only in a centralized place, in multiple places. And also to bring a lot of cost structure down so it can benefit general public. Now, if you look at commercial providers do not tend to take innovation unless there is significant amount of dollars attached to the services. Whereas the easiest way to change the mindset, essentially from a traditional IP networking background to an innovative platform, was to go through research and education networks. That was the primary focus. They allow innovation to come in with least amount of resistance. The idea over here is, instead of completely overhauling the existing infrastructure to an SDN-based network, allow the users to have an SDN-enabled networks and allow the users to put one service at a time or an SDN service at a time, overlap that on an existing network and do a hybrid environment. So you can do both. You can do traditional services for all your existing customers, and when the need arises, you can overlay an SDN service, an OpenFlow service, as the need arises. So your network should be capable of it. And as you transition and as the value-added services becoming more and more dominant, then you can transition the entire network into an OpenFlow service, into an OpenFlow-based network. Idea being that your controllers, your standards, the implementation, as well as how the OpenFlow network reacts or SDN network reacts, that has to be taken into consideration. It took 15 years for IP, MPLS, and Ethernet to be at a stage where it is. Reliance, availability.
Transition to an OpenFlow-based network. Is that the end game then for SDN in your mind?
No, OpenFlow is one of the basic structures of this stack or family of SDN networks, as we call it. You need some certain level, as I call, if you look at the OSI model and if you look at all the other structures in SDN, they're kind of looking similar now. So if you look, OpenFlow is one of the technologies which is at the base of this structure. If you don't have that, you cannot build some of the things, programmatic API interfaces, REST API interfaces, orchestration software. How do I build that infrastructure? I need something as a baseline. So that family of structures will be done only if an OpenFlow-based network or an SDN-based network is available, is reliable, and functions like today's service provider networks. Few use cases. We are primarily looking at 4 of the use cases: data center virtualization, WAN virtualization. We are also looking at analytics. Analytics is where you can programmatically say which flows are required where, and you can allow these flows in the network to go into an IPS or an IDS server. And then use these analysis to either do past analysis based on events, or you can do predictive analysis based on future. That means I know what my network did 10 days ago. I know an event is coming up, so how do I configure my network, either for the time of the day, or topology of the day, or bandwidth of the day. So I can repurpose my network for the same topology. And then finally, service creation and insertion. And this is primarily for tier 1 operators to drive service velocity. Right now, if you look at some of these tier 1 providers, they do tiered services, essentially flat phone plans to tiered phone plans. That means I have text messaging, web services. There are different types of tiers. And for different types of tiers, I need to actually authorize them. I have to actually detect them, send it to a local cache data center, wherever local cache is available, and then I have to finally be able to monetize it. Meaning that I know a user has X number of services, I know where to send it, I know the nearest point of location for the service, and then what do I charge for it. So service creation and insertion. For the WAN use case, the hybrid switch mode actually is a service where you can either build a complete OpenFlow-based network. That means you take a device, switch, router, doesn't matter, layer 4 to 7 application delivery, and then you say, okay, this device is only going to run OpenFlow. But that is not acceptable. It has to run traditional services also. So that's why you need a hybrid switch or hybrid router or a hybrid layer 4 to 7 device. I can carve that device out based on the ports I which one want to program. So there are some ports which will do traditional services, some ports which will do IP, MPLS, layer 4 to 7 services. But then how do I protect against each other? So what we did over here is to enable a protection layer, and that protection layer has to be done in hardware, meaning that it cannot look to controller, it cannot look to software services to actually figure out whether this protection can be applied to traditional IP services or not. What does this mean? What does this mean to a user in a WAN? Why is it needed? Now, if you look at 2 different structures for hybrid, there is a hybrid switch mode, there's a hybrid port mode. And in case of hybrid switch mode, this is what sometimes is also called to ships at night, meaning that there are 2 different entities inside a device. One is programmatic interface. For this purpose, we'll call OpenFlow. And there is a traditional interface or native routed interface. They will not talk to each other, but they will give each of them a given set of ports, a given set of resources, and they are independent of each other. A second option is to have a given port. The port itself will be carved out, meaning that it will carry a range of traditional services and a range of programmatic services on the same port. This is what we call as true hybrid port mode. And this is where the confusion arises in the industry. When you say hybrid mode, most of the people tend to look at hybrid switch. They do not tend to look at hybrid port. Question comes in, why is this so significant? If you look at the uplinks, this is where your cost is. For all the people who want to use this mode, if they want to connect to WAN, the cost is in the number of ports connecting to WAN, because the lambdas, the dark fibers, they are charged by the providers. In this case, if you're doing a hybrid switch and if you want high availability, you'll require multiple uplinks, thus significantly increasing cost. If you look at hybrid port mode, I can repurpose the same uplink for all the services. So reducing the cost significantly on that port itself.
I've seen 100 gig uplink modules cost, so yeah, that's not something you want to keep paying for.
Right, and then in this case also you have the WDM infrastructure,
Yeah.
which we haven't even touched over here, right? And this has to be programmatic. That means in this case the port itself is under control of multiple entities, and within the device itself now you're talking not only traditional routing services, not only traditional MPLS services, but you're also, in case of OpenFlow, you're saying there are multiple controllers available. So there are multiple entities in play over here for that port. And that's where the condition for a hybrid port mode control arises.
So I've saw these diagrams like this before, and one question that I have is, okay, so you have something on an OpenFlow control port that needs to access something on a traditional port. Is there logic between the two layers to allow, or is that going somewhere else and punting back?
Okay, so there are two aspects to the question. There are two entities over here, a traditional entity as well as an SDN entity. Who wins? Who should I give the control first? And the second entity is, even if I give the control, can I pass through from one entity to another entity, right? Meaning that, okay, I have for purposes of discussion here, I give SDN my first priority, traditional IP routing the second priority. It doesn't mean that if there are certain flows, certain routes, certain packets which come in, they go through OpenFlow first, and then if it doesn't know what to do, it just goes into a black hole traffic. It doesn't mean that. You have a choice over there. You can either say A, drop it over there, or B, give it to traditional guys or traditional entity and let it figure out where to send the traffic. So that's the control where both
So you have this working today?
Yes.
Right. So Cisco told us yesterday that this was really hard and they didn't want to do it. Remember? Just to point it out that,
John said,
you know,
I didn't say that.
I did, right? Just want to draw that out. You know, we had that guy yesterday.
So we have a national backbone working on this one.
I think they said if the industry does this, they'll do it.
Well, and so,
If they can find a customer who wants it.
so just because the ONF's hybrid working group dissolved and didn't produce anything, doesn't mean there aren't, we've got the OpenFlow normal primitive that's there that says, when you come out of it, if you don't match in the SDN pipeline, the OpenFlow pipeline, you're gonna match into the normal pipeline, drain into it. It's your default flow for your, the traditional default route.
Right.
Well, and the unique thing that Brocade brings is they can flip that pipeline, right? So they could say, well, I want you to go in the normal pipeline first, and then I'm going to go into the OpenFlow pipeline. So that's something unique to Brocade that everybody else needs to be looking at, because this is the ease it in. Patches of green, as Greg puts it.
Yeah. But Cisco made a big point yesterday that this was really hard and no customer wanted it.
Yep.
And they didn't feel that it was a feature that anybody wanted.
So what you may wind up with is something that's interesting, I was just thinking about what you just said, is, okay, so you come in and look at your traditional, if there's a default route, let's say it's a layer 3, but you may want to actually break that into two pieces. Let me look for the specifics, then go to OpenFlow, and then finalize defaults.
Yep.
And you may want to have some
Exactly.
level of control like that.
So when you hear you only support 100 rules or 1,000 rules or 2,000 rules, that's fine, because whatever your early application is, you should be able to proactively match that. So you proactively instantiate it there. You don't have any performance issues at that point because you're not punting off to a controller. I mean, firmware bugs need to be worked through, but everybody's going to have that early on.
Yeah. You can do a lot with 1,000 flows, right?
Right.
If you have very coarse flows,
Right.
like routing flows. Like the whole 10 dot is one flow.
Yes, like the defaults.
Yeah.
Big summarization.
So, if,
Or you could have it like in the G-scale network where a flow is Gmail,
yeah,
the gigantic flow, right?
yeah, absolutely
Plus
enormous flow.
button.
So
Yeah.
it's one of those things that people don't always think about. They want to hear, like, you've got 1 million flows in a table because you're going to route every IP address. As if you're going to route every IP address individually. You're not. You're going to route like an ordinary network, which is 1/24 subnet, 1/26, /20 subnet, that's one flow. So if you have 1,000 flows, that's actually quite a lot.
Not really, because, the internet routes are aggregated, and there's about, if you look at route views, there might be
Yeah.
350K right now.
Sure, but we solved that with MPLS, right?
Not for those people who have to carry full routing in the internet.
Yeah, I know. Yeah, I'm not saying that the world isn't, it's not solved, but 1,000 flows is actually more than most people think. You can actually solve real world problems with 1,000 flow entries in a table.
Yeah, no doubt.
Yeah.
But you can take an OpenFlow switch and do 10 stars or 12 stars saying, I'm going to match everything on here. My action, I'm going to match on everything. My action is normal. OFP normal. Turns it into a normal switch. You're going to flood,
Yeah.
you're going to forward, drop.
Sorry.
Right, so here the assumption is, there's a big assumption. Here the assumption is that the switch is OpenFlow capable. It defines to a normal standard, which is defined by the OpenFlow 1.0 standard, and it has an ability to change that function to the normal pipeline.
Yep.
Sometimes, I would like to point out, modular platforms and one RU or single U platforms are completely different in the way they behave. Single U platform usually have pipelines which are built into the chip itself. It's hard to change the pipelines when it's built into the chip. If you have a modular platform and with FPGA support, you can change the behavior of that pipeline. So, protected versus unprotected. Why do we need it, right? Now let's say, for example, if you were to have a flow, a VLAN, a subnet, whatever the entity might be in the traditional sense, that entity can be controlled from a controller. So for example, I have a flow, I have a route, and my OpenFlow controller says, hey, guess what? I will change that route no matter what my IP route table says. Or hey, guess what? That MPLS label, I'm going to go override it. How are you going to protect your existing network? So what you do is, you say some of the VLANs, some of the routes, some of the labels are protected. And straight away, they're not going to listen to OpenFlow at all. Meaning that no matter who takes control of your OpenFlow controller, whether it's the device or the IT guys within your department, or whether it is a hacker which has taken care of the controller, you're still going to protect your traditional network, because that will be driven by your traditional routing protocol. So all your firewalls, all your route maps, all your routing policies will stay in effect for that particular VLAN, for that particular route table, for that particular MPLS table. So there's a difference between protected hybrid port mode versus unprotected hybrid port. Now what does the flow entry look like? Everybody knows who has seen this OpenFlow. This is a well-documented slide, but we have seen subtle differences in this one. Because we have implemented hybrid mode, because we have put in a national backbone, because we are in multiple places where we have done this OpenFlow rules. And the subtlety is this. First, I would like to point out that VLAN ID is actually just a field. Most of the places have said that VLAN I need to repurpose on every single port. Meaning I have a set of VLANs, 4K VLANs or a specific VLAN, it has to be local to that particular port. Meaning that VLAN 100 on a given port can be reused as VLAN 100 on a different port. So it becomes just a field. Now what the interesting use case is, a major content provider, sports channel, has said, how can I use this? And the idea is not to multicast sports channels across the network. You have to unicast those sports channels across the network. So you take away all your multicasting capabilities, put them in OpenFlow, and give a point-to-multipoint connection where the device is able to reuse that VLANs on the fly. And you can do that with OpenFlow today. You can take your entire multicast topologies and turn it into unicast topologies, meaning that replication will happen on demand and will happen in an E-tree fashion, depending on where the root of replication is located. So it's hierarchical. Okay? The second point is, just doing layer 2 matches is not going to cut out. You need a match which is encompassing both layer 2 as well as layer 3. But when you do layer 3 matches, you definitely don't care most of the times don't care about the addresses, MAC addresses. What you do care is about the VLAN as well as the priority on which that VLAN is riding. For example, queue in queue, extension of VLANs in metro, or either trusting or untrusting that priority where the VLANs is going. So in that case, you have to match certain layer 2 fields with layer 3 fields. So there are certain subtleties when it comes to matching all sides of the coin over here. The device or the platform itself, it should be flexible enough to give you that particular role, meaning that you can either do layer 2, layer 3, layer 2 combination with layer 3, certain portions of layer 3 only, or certain portions of layer 2 only. So that flexibility has to be there. And OpenFlow does allow you to give that flexibility. However, the rule itself will encompass all the fields itself. Okay. Brocade's approach to OpenFlow, I'm going to cover only a couple of things over here. We support both commercial as well as OpenFlow controllers, meaning open source controllers, whether they are NEC, entity data, as well as Floodlight. We also do knocks on flow visors for proxy controllers. What is our unique position? Our unique position is that we do not believe in software licensing. All our flagship platforms will actually come with this programmatic capability built in. Anybody and everybody who has this platform just has to upgrade the code. They will get SDN into the networks. Now, remember when I said most of the WAN providers are running on this platform, guess what will happen when they change it? Automatically, this capability is now built into the WAN itself. Whether it's hybrid mode, whether it's hybrid port mode, switch mode, or standalone mode. You have an option to run this across WAN. Second is, they have to be based on FPGAs. There is a big differentiation between merchant silicon and bringing the commodity price down. True for top of the rack aggregation devices in the data center. Okay, not true in WAN. WAN, you need programmatic interfaces, but they have to be based on FPGAs, which will allow you to bring in evolving standards, whether they are encryption-based, security-based, or algorithm-based. You need FPGA-based systems to allow these standards to come into play. And lastly, you do need wire speed performance without compromise. You do not want to say, oh, by the way, I support 100,000 flows, but only 700 are only capable of doing in hardware. Rest of them are going to go in software and will take your CPU switch down. Meaning that the processing power on the CPU is going to go through the roof. You do not want that kind of capability on a WAN infrastructure platform. So you need a high number of flows as well as the wire speed performance characteristics of it.
So you're saying that's where things are headed as far as the performance, that's where things are in the Brocade MLXe right now?
So on the WAN virtualization use case, these are some of the criteria, and this is why we built that platform with the OpenFlow support on this.
Yeah, and so to say that FPGAs are the only way to implement OpenFlow?
No.
Okay.
No. I'm saying there are multiple evolving standards.
Too, yeah.
Correct. There are multiple evolving standards. Whether it's SDN, if you look at the whole stack, there are multiple components to it. So when you start bringing in these components, you need that flexibility in the platform. This is a way to do it. This is one of the ways to do it.